Okay, so the idea behind the second lecture is to talk about a different kind of high-dimensional multivariate normal that's easy to interpret, which is when the precision, what's called the precision matrix, is sparse. So the precision matrix is the inverse of the covariance matrix. So last time we looked at low-rank covariance matrices and how they can be kind of easy to interpret. Now we're going to look at a different structure that makes the multivariate normal particularly easy to interpret, which is when its inverse covariance matrix, its precision matrix, is sparse. Okay, so that's in this vignette here, this normal Markov chain vignette. So basic idea is we'll come across the precision to begin with, right? So here we go. So omega here is the precision matrix, okay? And it's just the inverse of the covariance matrix. And it turns out that it has this very kind of nice property, here, that sigma omega ij is 0 if and only if xi and xj are conditionally independent given all the other coordinates of x. So it's got connections with Markov chains and Markov models because of this kind of conditional independence. Markov property is about things being conditionally independent given the previous state, for example, or in a general Markov chain, an observation at time t is conditionally independent of the rest of the chain given the observations at time t plus 1 and t minus 1. So we're going to see here an example of a Markov chain actually to start off with, to illustrate this idea of conditional independence. So of course, you know, the covariance matrix is 0, ijth element is 0 if and only if xi and xj are independent when they're normal. So 0 covariance means 0 correlation means independence in the normal case. But the inverse covariance matrix, which is kind of a more complicated thing to think about initially, the zeros of that matrix also have a really interesting interpretation, right, which is conditional independence. Okay, so let's look at an example which is going to make this clear, I hope. So this is a Markov chain where the transitions are just a random normal. So xt plus 1 given xt here is just normal centered on xt with variance 1. So the idea is that wherever you are now at time t, xt, you just add a random normal to it to make xt plus 1. Okay. So here I simulate this Markov chain. So we just, x is going to be just a vector of length, in this case, 1,000. And then the first element is just a random normal, and then each time I just add another random normal to it, right? Xt equals xt minus 1 plus a random normal. Okay, so that's what you get when, or that's what I got when I did this. So the index here is time. I think it's time. We started as a random normal 0, 1. And each time we've just added a random normal. And in fact, this kind of is doing something called Brownian motion. Okay, it's this kind of wiggle. Okay, so the funny thing is, maybe you might not be used to thinking about it this way, but this is actually a draw from a 1,000 dimensional multivariate normal. It's just one draw from a 1,000 dimensional multivariate normal. Right? x1 up to x1000. Their joint distribution is multivariate normal. So how can we see that? Well, why? We can write down the z's as let z be those random normals we generated at each step that we added to the previous step. So x1 was z1, and then x2 was x1 plus z2, which of course is z1 plus z2. And x3 was x2 plus z3, because z3 is the change from 2 to 3. So that's just the sum of the z's. And so you can see that xt is just the sum of all the z's up to time t. So we can write that in matrix notation like this, where A is this matrix. The first one just picks out Z1, the next one is the sum of the first two Z's, etc. So we can write X equals AZ, where Z is a multivariate normal. The vector Z now is multivariate normal with IID standard normal entries, right? Normal 0, 1. So that means that X is normal A transpose, right? So yeah, that's just coming from, we looked at this, well, let me start again. So that's just coming from the fact that if Z is normal 0 IP, then AZ is normal 0 A transpose, right? Where this is M by P and this is P by 1 for any A. In this case, A is a 1000 by 1000, so it's actually a P by P. Yeah. Yes, okay. So that's where that comes from. No, that wasn't what I meant to do, sorry. Go back to the okay, so what's its covariance matrix? Well, it's AA transpose, and here it is. If I just do compute AA transpose, sigma equals AA transpose, and I plot it, it's got a very interesting structure, right? It's got ones on the first row and column, twos on the next row and column, threes in the next row and column. Not surprising because A had a very kind of strong structure as well. So it's not surprising that this is structured, but it's you know, not a low rank matrix, and it's not a sparse matrix. So it's not, looking at that, it's not that easy to see. You know, if I told you, you know, you've got a multivariate normal with this variance covariance matrix, maybe you wouldn't have immediately thought of it. Oh, it's just Brownian motion. Okay, but let's look at the precision matrix now. Okay, so we're just going to take the precision, the inverse of this matrix, and look what it looks like. It's got lots of zeros in it, and that's because of this conditional independence property. Remember that omega ij is 0 if xi and xj are conditionally dependent given all the other xi's. Okay, and for a Markov chain, xi and xj are independent. Sorry, for a Markov chain, right? x1, x2, x3, x4, let's say, maybe, etc. So x4 can, given all the other x's, x4 depends only on its neighbors, x3 and x5. But that's an elementary consequence of the Markov property. Right? X4, given its past, depends only on x3, but equally, it's true that x4 given the future depends only on x5, and x4 given everything else is dependent only on x3 and x5. So what we expect is that the element, if we look at the fourth row of the precision matrix, it will have zeros everywhere except for the locations 3 and 5 and actually at 4 too. Okay, so it's the off diagonals that have this kind of. So let's look at it again. If we look at that, sorry, omega, and we look at the third row, look, it has, sorry, the fourth row, it has entries non-zero only for the third and the fifth, and its own fourth element. The diagonal is non-zero as well. Okay, so the idea here is just to get your head around the idea that the precision matrix tells you about conditional independencies, and that can be a useful way of thinking about data. In fact, the way that people sometimes think about this in terms of Gaussians is to think about your x's in general. Not, there won't necessarily be a Markov chain, but imagine that you've got, you know, a large number of x's, many more than 5, but I'm not going to draw them all. And the idea being that some of them are dependent on one another, even given the others. So people will draw a graph like this, where the line between two nodes indicates that the omega ij is not equal to 0. So if there's no line, omega ij is 0. If there's a line, omega ij is non-zero. Now, of course, in general, we don't know what omega ij is. We're given data, so we get observations, and people try to infer from the data which elements of omega ij are non-zero, and they interpret those non-zero elements as meaning that those two nodes are kind of connected in a graphical model. So these are sometimes called undirected, so the edges here, Gaussian graphical models. An example of methods, if you're interested in reading more, would be the Lasso, which is like a graphical version of the lasso. And basically, it involves doing things like regressing x4 on all the other x's and seeing which coefficients are strong, let's say non-zero, and drawing an edge from x4 to those. You know, if we regress x4 on everything else and the main predictors of x4 are x3 and x5, we would draw these lines here to connect x4 and x5, because that regression exactly tells you that x4 is conditionally dependent on x3 and x5 given everything else. You know, if you regress x4 on everything else, then the significant predictors in there are exactly the ones that it is not conditionally independent of, right? That it's conditionally dependent on, because that's what a regression is looking for, is conditional dependence of y on a predictor, right? So you just do that for each node in turn, if you like, and find the significant edges, and you can imagine that maybe you get some contradictions where when you regress, you know, the different regressions might not completely line up, and so, you know, but the idea of doing that using the lasso is called Lasso or Graphical Lasso. So the idea there is that you can kind of build up a picture, a graphic that maybe tells you how your different variables are connected to one another or not connected to one another in a network. But it's based on conditional dependence rather than just dependence, marginal dependence. Because in this network, everything will be dependent on everything else because everything's connected, right? So if you looked at sigma, you would get kind of a complicated sigma, just like in, you know, in our example here, the sigma was dense, right? If you looked at that sigma, you wouldn't immediately see, oh, it's Markov, right? So looking at the structure of sigma, I mean, obviously it's super simple. You might recognize it. If you see it in the future, you might recognize this one. But in real data, the empirical covariance matrix you might get from data won't be super simple like this. It's going to be noisy and complicated. And so people are trying to, maybe if you look at even if you look at the sample inverse precision, the sample precision matrix, in fact, that often doesn't even exist because often the covariance matrix isn't invertible. The sample covariance matrix isn't invertible. So you have to do some kind of inference to get to the precision matrix. But still, if you can infer a precision matrix under the assumption it's sparse, then you learn something about the connection between the variables. So in this case, we might have learned that that the x's were connected via a Markov chain. Should be said, we couldn't do that based on one observation at each time point, but imagine that you had, at each time point you had observation on 100 different variables. Maybe they're stocks, 100 different stocks at time point 1, 100 different stocks at time point 2, 100 different stocks at time point 3, and you could start to learn about the conditional independence of those observations. Actually, there's a more kind of a stronger statement. It's not just, we focused on the zeros here, but there's actually a conditional mean, that the quantitative values of the omegas actually have of the non-zero omegas actually have an interpretation. And that is, in terms of the regression coefficient, you would get if you regressed one on the other. So here's the general statement here in this addendum. So here y1 here is in this statement here, y1 is any subset of x and y2 is the remaining subset, and omega 1 is the, yeah, I guess I can draw it out. So so I've got x equals y. I'm partitioning it as y1 and y2, and I'm partitioning omega like this, right? So that's what's going on there. And so the statement, oh, yes, sorry. So the statement here is that you could predict any subset of x's, the y1s, from the remaining x's, y2s, by looking at these coefficients, the 1 over omega 1, omega 1, 2 times y2. So actually, in this case, there is a generalization. I guess in this case, y1 is just the first coordinate of x, and y2 is everything else. Sorry. So y1 is a one-dimensional part of the x. Sorry. So the way I drew it was general, but so 1 over omega 1 is just a scalar in that case, right? Okay. So if we just apply this formula to get a bit more intuition, so if we want to look at the conditional distribution of x1 given all the other x's, we can look at the first row of the precision matrix. Basically tells us what would we get if we regressed x1 on all the other x's. What would their coefficients in that regression be? So the first row there, and the zeros say that those x3 up to x1000 in this case would get 0 weight in that regression, and x2 would get, remember the formula here, 1 over omega 1, omega 1, 2, negative of. So in other words, it would be a half, right? Yes. Omega 1 is 2, so you get a half of negative 1. Take the negative of that, you get a half. And the second line of omega here would similarly give you the regression coefficients for if you regressed x2 on everything else. So if you were trying to predict, think of it this way. If I gave you all the x's except x2 here, all the x's except the second one, and you wanted to predict what x2 was, that is, what's its conditional mean given everything else, the answer would be given by the elements of the covariance matrix. Actually, if you read off the equation, it's a half x1 plus a half x3. So actually, that's a very intuitive rule, right? If I give you, and in general, xt, if it's not at the end, xt, given all the others, you would predict it by the average of its neighbors, right? So that's what this that's what this precision matrix is telling you when you apply this rule here for the conditional expectation. So that's what this is about. Okay, and that's going to be important when we talk about Kriging next time. So it's going to come up again. All right.